first of all, welcome all to again another UCAR Africa seminar. Seminar. My name, for those who don't know me, my name is Ana del Moral Mendez, and I'm part of the UCAR Africa Initiative Working Group, and I'm working as a project scientist at the Earth Observing Lab here at NSF NCAR. I know that also in the call is Wenfu, who is also part of the initiative, and it's the lead PI of the initiative now, and working in the ACOM lab here also at NCAR. So today we are hosting the session titled Understanding the Causes of ITCZ Stagnation in CMIP6 Models. And we're pleased to present that our speaker today is Tombizibe Cephas Dombo, who is a principal meteorologist at the Nigerian Meteorological Agency since 2011, and is working as an aviation weather and pilot briefing meteorologist. Tombizibe is about to defend his PhD, if I'm not wrong, in atmospheric science at the Indian Institute of Technology in New Delhi. And he's interested in weather and climate change dynamic simulations and in climate modeling. He's looking for his next step in his career and willing to find a postdoc position in tropical weather storm tracks like African easterly waves and their future track changes using Lagrangian methods. And he's also a member of the American Meteorology and the Nigerian Meteorological Societies. So Tombizibe, thank you so much for being our speaker today in the seminar series. Just as a reminder, you now have about 45 minutes to present your work to allow for some questions at the end. And for all of those who are in the audience joining today, please submit your questions for Tombizibe through Slido, and we will read them and answer those questions during the Q&A session at the end. So please, Tombizibe, welcome, and the virtual floor is yours. So whenever you're ready, just go ahead.
Yeah, I'm ready. Thank you very much for the great opportunity and for the privilege to have this beautiful discussion with everyone. This discussion is going to be based on understanding the causes of ITCZ stagnation in CMIP6 models. And this discussion is actually based on one of my papers. You can find that online, and this is the title, and you can find time to digest the paper if you want. So by way of introduction, want to know what is the ITCZ? The ITCZ is the position of, the position of the ITCZ is actually related to the seasons of the year. An ITCZ is actually defined as a place of convergence between two trade winds, southeasterly trade wind and northwesterly trade winds, which actually varies with season. So in January, mostly it is southwards, although over Africa is not below the 0 degree north or latitude, but in July it goes as far as close to 14 degrees over the northern African region. So the northward migration of the ITCZ, which is also the intertropical convergence zone, is a significant feature of the African monsoon. Please understand that the ITCZ is also related to precipitation, how northwards precipitation also goes and how southward it goes, but mostly is defined over Africa as ITD, the intertropical discontinuity, where you have where you have the two trade winds, the two major trade winds where they coincide, and then you have zero absolute vorticity. So the accurate simulation of ITCZ migration is essential for the realistic presentation of African precipitation in global couple models. So in this seminar, we actually try to see the dynamic frameworks and the energetics using a subset of CMIP6 models. CMIP6 there stands for Coupled Model Intercomparison Project. The phase 6 of that project, we are looking at these models to investigate the biases in the simulated migration of the ITCZ and the precipitation over the region of Africa. Now, the fluctuation in summer monsoon rainfall can actually affect, various aspects of the Saharan African life. And therefore, the current generation of coupled general circulation models have varying degrees of skills in simulating the precipitation in the African monsoon rain belt. And we know from literature that the intensity and frequency of precipitation are expected to impact the economy of the region, not just Africa alone, globally, and can also create water scarcity and food security challenges. And therefore, the reason why we need to look at models is so that we can get reliable projections in future climates. So the skills of this model in the ability to simulate the present or current characteristics of precipitation, it's very, very important to give us confidence in the future projections that we may have and may be going for. Don't mind the right-hand side, very bogus, right up there, but I'll explain from the figure you can see on the left-hand side. So if you look at these models, you see these numbers are just in front of this text. You have historical. There are about 51 models being analyzed for global temperature change between the current and the future climate. And then you have SSP1 to 1.9, you have 11 models and so forth. Now, below here is the axis that shows the years in which this computation was made from 1950 till the 21st, end of the 21st century. So this has been divided into three major parts. You can see it in the near term, the mid term, and then the long term. The long term actually is from 2081 up to around 2080 to 2100. So you can see that the black line here indicates the historical period. You can see from the historical period up to 2000, above the 2000s, there is, a cross line here, a threshold line, which is the zero mark. There is an increase in temperature. So that's to say that the global temperature is increasing, and then in the further future, it's expected to further increase. So based on all these social economic scenarios that has been depicted in CMIP6 models, now you find that especially in SSP3 to 7, and then in SSP5 to 8.5, most models show that there is an increase in temperature. Now, how about the global precipitation change? So the change here is with relation to the historical period. On the right-hand side, you have the relative to 1995 to 2014. And then on the left-hand, at the bottom, you have the years. So relative to 1995 to 2014, which is the historical period indicated in black here, you see that also precipitation is expected to increase over the land globally. And then in September season, the Arctic ice is also seen to be decreasing over time. So as you have increase in precipitation, increase in temperature, you have an increasing change in precipitation, and then you have a decreasing change in Arctic sea ice. And then how about the global mean sea level change? You also see an increase in the global mean sea level change. So with this, we now understand why it is important for us to look at the future precipitation and understand if these models are able to capture these scenarios, especially in the migration of the ITCZ as depicted in this study. Now, we look at some selected indicators of global climate change on a spatial scale this time around, a 3D dimension. We have looked at the 2D in terms of time. Now we are looking at the 3D dimension, a 2D dimension in terms of space. So if you look at the over Africa at an increased temperature, in an expectation of an increased temperature by 1.5 degrees Celsius, we can see that there is higher warming or stronger warming around the Arctic region. If you can see my cursor around the Arctic regions over the land in the northern hemisphere, and a decrease on the southern hemisphere. Now you look at this little patch over Africa, you can see that there is also an increase in temperature in the future. Okay, then on the right hand side is the precipitation, and then you see that there's precipitation will increase in higher latitudes. Okay, now the color bars are shown at the bottom side here. You can see this is for 1.5 degrees above, and this is for an increase in temperature of at 3.0 degrees Celsius, and this is what we have. So overall, we can see that, especially over Africa, you can see that there is going to be a wetter scenario of greater than 40% precipitation change, around the tropical regions of Africa, and then some in the Pacific Ocean. So that's to tell us that as the temperatures increase and the average warming of the surface also increases, then precipitation also increases. Now, I want to narrow down to Africa itself and then use that as a study area for us to understand better the subject that we're discussing now. On the left-hand side, you find the spatial mean of June, July, August, September distribution of temperature and the mean sea level pressure. And now this is from NCEP NCAR data set from 1980 to 2020. So a period long enough for us to have a climatology. Now you find that over the northern region, above 15 degrees north, you have high temperature. At the same time, you have low pressure belts. So you can see where you have the peak temperatures, there you have the low pressure areas. Now, just a little below this is where you find precipitation. So precipitation follows the order of temperature. Now, below here is the Hofmüller diagram indicating the latitude and time in terms of months, distribution of the mean sea level pressure, and then temperature. So this is just to give us an idea of how temperature migrates in the season. So from January to December. Now you can see that within this May, June, July, August, and September, you have the core of temperature, the height of temperature. I mean, the maximum temperature values are found around there. And then you can also find the mean sea level pressure is low. So the lowest mean sea level pressure is also found within this area. That's to tell us that mean sea level pressure corresponds or correlates strongly with temperature. Now, on the right-hand side, we now look at the annual cycle of precipitation and surface temperature, specific humidity, zonal wind and meridional winds, which have been averaged over the study area for a period of 1995 to 2014, except for TRMM, for which the data set is just between 1998 to 2014. So the area we have averaged is just between these areas on the map on the left that you can see, and a little further to the west, around 30 degrees west up to around 50 degrees east, and then from 15 degrees south up to 15 degrees north. So this is what we can see. The dotted lines indicate GPCP precipitation, and then the black line that is also short indicates the GPCC, and then the full line indicates the TRMM for precipitation. Now you find that some models overestimate precipitation while some models underestimate precipitation. We'll see the reasons why these are occurring, but in all, you can find that there's a gray line, shaded gray line, vertical gray line here between June to September. So we can see that most models show this, and some models also show this by, these bimodal distribution of precipitation, as you can see. Then temperature also shows a little bit same conditions. You can see low temperature here, high temperature here. So also giving us a kind of example of how precipitation and temperature also relates. Now you can see also that most of the models overestimate temperature in the region. And then specific humidity, some models underestimate while some models overestimate. Same thing with zonal winds and meridional winds. within the region. You can see there are peaks. So all these activities happen within this season, and that's why most of the studies we're going to consider are going to look at more or less the JJS, which is more or less the monsoon season that gives us rains within the region. Now, the monsoon has its positive and its negative consequences and advantages. So the advantages are that when the monsoon is in moderate order, it helps agriculture, it helps water resources, it helps the ecosystem to flow properly. But when the negatives of monsoon are experienced, it can lead to flooding. Animals, humans can be affected, plants can be destroyed, sometimes can lead to, forced migration. It can lead to drought. If there is less monsoon, can lead to drought, and animals, humans can suffer from this. And then if it is excessive flooding, then we can have deaths due to waterborne diseases. So, for example, in one of the years, in especially 2022, there was a general report over Nigeria that more than 600 people have been affected due to flooding, and more than 1.3 million people have been displaced over the region as a result of flooding. So this is not only particular to this country, but across the world, across the monsoon zones, monsoon regions, extreme events due to monsoon, more rainfall and flooding are causing large amounts of displacements and deaths and other forms of casualties. And that's why we are focusing on the monsoon season itself. Now, I have initially defined the box in which we are considering in this study. And then basically we're going to look at 1995 to 2014 for most of the models. And then for TRMM, which is the base data set we are using for precipitation, we're going to consider that between the period of 1998 up till 2014. Now, on the right-hand side is just an indication of how well the models are performing in simulating the precipitation between June to September months. Okay, so the green bars indicate the root mean square error, and then the black bars in this box indicates the pattern correlation coefficients, that's the PCC. And then on the right hand side is the skill score. So the skill score is computed between the ratio of RMSC and the pattern correlation. If we look very well, you can see and observe that there is a decreasing trend in the skill score. So this has been arranged in the order of the skill scores. And so you can find better models having greater skill score, and then the worst models having lower skill score. So to narrow down and to get objective about the study, we try to differentiate between the first 5 models and the last 5 models and see if there is a uniformity in the simulation of precipitation in these models. In our study, we have seen that spatially, the models are performing very well. In fact, you can also see that the PCC shows above 50% of pattern correlation between the observation and then the models. That's to show that generally the models are doing fine, but then to what extent can they be compared to observations? And that's what we are going to look at here. So in this computation, we have used about 26 models in all, with resolution of about 100 kilometers to 250 kilometers. We have chosen one simulation per model with a variant of, with the first variant and first variant label. And then we have looked at the 20-year historical period from 1995 through to 2014. Now, we have also used some other data sets like the tropical rainfall measuring methods. We have also used the ERA5, and we have also used hard ISST for the sea surface temperature measurements. And then for the shortwave cloud radiative forcing that we may be computing later on, we have used the Series EBAF method and Series EBAF dataset between 2000 and 2021. So even though these values are showing they are different, I mean, these dates are different, 2000 to 2021 and 1995 to 2014, from our analysis, we have found that there is no significant difference or significant change when we consider this period and the other period, because we have tried to look at the corresponding periods and then the entire period and see that there is no significant difference. Now, I come to precipitation asymmetry. What is precipitation asymmetry? Precipitation asymmetry simply gives us the, a kind of analogy that we can use to describe how precipitation, moves from the south to the north. So it's also an indication of showing the migration of precipitation. How does precipitation migrate from south to the north, from one season to another season? So it's more or less a proxy for us to understand the migration of precipitation during the monsoon season. So this also has been done within the study area, and then it's calculated between by the zonal average of the difference between the northern hemisphere and the southern hemisphere, and then divided by the area average between the northern hemisphere and the southern hemisphere within the region of study, okay? And what do we find? What we find for precipitation is that in TRMM, remember TRMM is the observation, we find that the mean distribution of the precipitation asymmetry index is very high, okay? But then consider the multimodal mean and the best models. The best models are the subsets of 5 models from those that have very good skills. And then the worst models are those from the models that have low skills in simulating the precipitation over the region. Now you find that during the JJS period, there is a negatively skewed mean in the worst models compared to the multimodals and then compared to the observation. And then also you can see a very strong shift between especially the models, multimodal mean, and the worst models, and also between the best model and then the worst model. So this is what we are considering right now. And so you can see this is an indication that these worst models are not actually propagating to the north within JJS season. They're actually supposed to move ahead, move upwards or northwards. And so we're going to understand what is the cause and why are these models not properly showing that migration. Why are they not measuring up? At least we can see that the best models are a little close to the observations, but the worst models are pretty much below expectation and even negatively skewed in their mean distribution. So now I want to show also a kind of interhemispheric asymmetry of precipitation. This is just a computation of the difference between north and south, okay? So between 0 degrees, any variable, I pick any variable between 0 to the northern hemisphere, any location in the northern hemisphere, then the difference. So I'm computing the difference between the two, all right? But before that, I want to show us the mean distribution of ITCZ location, the latitude of the intertropical convergence zone within the 4 major seasons. DJF represents December, January, February. MAM represents March, April, May, October, November, which is around the dry season, and then the JJS, which is in orange color. JJS there stands for June, July, August, September. Now, if you observe very well in the TRMM, let's just see TRMM, for example. You see DJF, which is December, January, February, which is often referred to the dry season. ITCZ is usually down south, just like we have said in the introduction. And then it continues to progress March, April, May. You can see in this gray color. And then in the green color, it has further gone upwards October, November, and then in June to September season, which is the monsoon season, we can see it up north. Now, if you compare the best models, okay, I come here, if you compare the best models and then the worst models, you will also see that signature of skewed distribution, or the models are not migrating, they are sort of stagnant, they are not moving up. So this is the bedrock of the discussion today. Please follow me along as I show you the zonal mean distribution of precipitation, and then the interhemispheric asymmetry that we can see. Now you observe that most of the models are showing excessive rainfall between 5 degrees south and 5 degrees north, and then there is a large difference north of 5 degrees in precipitation. So this shows us, you can see this is northern from 15 degrees south to 15 degrees north for precipitation. You can see that tendency for precipitation to be collocated on the south, okay, in comparison to the observation. The observation is in black, multimodal mean is in red, the blue lines indicates the best models, and then the green lines indicate the worst models. Now you can see that the worst models are even showing further south compared to the observation and the best models. Okay, so that you can see in most of the analysis shown here. So here on the right hand side, the B portion shows the interhemispheric asymmetry, and then you can see that the worst model is showing southward pattern compared to the observations and the best models. The best models indicated in the black here, you can see. So there is this southward bias of the precipitation in the models compared to the observation and then the best models. Now, one important difference we can find in all these variables that we have considered, this is the surface temperature, and E is the specific humidity, and then the bottom row here shows the shortwave cloud radiative forcing. So the shortwave cloud radiative forcing is actually the difference between the all sky and then the clear sky, you know, forcings. So here you see there is an excess shortwave cloud radiative forcing south of 5 degrees, you can see, and then there is a large difference south of 6 degrees. So if you look at this portion, this is where our focus is going to be. Now, if you look at the interhemispheric asymmetry between the models and the observation, you can see this large difference. It means that the models actually have some strong bias in their depiction of the shortwave cloud radiative forcing that is necessary for the balance in the atmosphere. Now, we look at the dynamic and energetic processes. Look at the spatial plots. You find the best models, the difference between the observation and the best models, you find a kind of bias, dry bias and wet bias, dry bias over the northern region and wet bias over the southern region of Africa. Mostly between 10 degrees north and about 5 degrees south, you have that bias. But then look at the difference between observation and the worst models. You find a stronger bias over land. That's more dryness. Models are showing greater dryness. This has actually been investigated in many studies. And then here it shows stronger wetness in the model. So there's significant bias in the worst models compared to the best models. Now come to B, which is the sea surface temperature patterns. Now this region, I call this region the CETAL region, that is South Atlantic region, okay? Southeast tropical Atlantic Ocean. That's where I call this region. If you look at the comparison between the best models and the worst models, you find that there is excess shortwave cloud radiative forcing in the worst models compared to those of the best models. Okay, so how about the distribution in the Hadley cell circulation? Now, one interesting thing we can see here is that we have used the vertical velocity to identify the Hadley cell circulation. You can see these vectors here indicates the winds. So the upper arrows, wherever you see arrows showing up, they are matching mostly with the blue shades, indicating an updraft, that is moisture and upward draft of vertical uplift of the air. Okay, so on the right hand side is for the worst model. On the left hand side, we have the best models. What we observe is that there is stronger downdraft within 5 degrees to 15 degrees north. which is about the areas that we are considering over here in precipitation. You can see this in the WASP models, and that is also reflected here. And you can see there is less of that in the best models, and that's also reflected here. So we can find stronger updrafts in the best models and then stronger downdrafts in the worst models. Now, the SST bias induced hardly cell circulation is what we can find in this story. Then let's look at the sea surface temperature depiction. We can see that strong SST biases set up around this region, Sidsatu region, especially in the WASP model, shows that the precipitation change driven by the decrease in land sea temperature contrast is one thing that we should take note in this study. Now I go to this moist static energy. So the moist static energy is also another proxy to tell us the migration, or how moisture moves into, or how there is this the buoyancy in the region, or the stability of the region is. So the more stable the region is, the lower the pressure in that area, and then the high pressure regions gives you a most sorry, I mean to say the areas where you have higher, vertically integrated moist static energy gives you areas with, more updraft, gives you areas with more moisture, gives you area with more convective activity. So we can say that the moist static energy is a proxy for convection, okay? So even though we can use OLR, we're using moist static energy in this case. So here you can see in the best models, I just moved to this axis. It shows that there is a form of strong vertically integrated moist static energy. And then if you compare that to the WASP models, you see that over the land it is reduced, and over the ocean it is stronger. So we need to take note of this, the track of events in this study. And then you can find some contours here in gray colors. If you can see, these gray colors indicate the zonal winds, okay? Zonal winds at 850. Okay, so this zonal wind is an indication of the strength of the wind within that period, or within the season, JJS, that we are considering now. So we expect more of southwesterlies within this region. So you find that the southwesterly winds over this the best models are stronger than those in the worst models. So that gives us the circulation characteristics between these two groups of models we are considering, and then the moist static energy component. Now, looking at this in a different perspective, same thing, we have looked at the spatial component. Now we're looking at the mean across the different atmospheric levels. If you look at mostly look at the best models, you find that there is an incursion of, the moist static energy even up to around 400 joules per kilogram. Okay, 400, sorry, up to 400 hectopascal level. But then you look at the WASP model, you see there is an inhibition of convection. So convection is inhibited here, like I've said, is a proxy for convection. But then if you look at between the equator, 5 degrees to 10 degrees north, or 15 degrees north, you can see it is not as pronounced or as deep as those in the best models. Now, looking at the mean of the meridional wind profile, we can see similar characteristics. You can see for the best models, the meridional wind shows strong southerlies, especially over the 10 degrees, about rather 5 degrees to 15 degrees north, than it is shown. You see more of northerlies in the WASP models. And these northerlies actually inhibit or prevent the growth of clouds and prevents, moisture updraft. So please take note of that as we continue. Now, don't worry about this figure. I'll just give a summary of what this figure says. When you go to the paper, probably you will get a better grasp of what this figure is talking about. So in this figure, we have divided the regions into 4. Okay, so we have from 18 degrees up to 40 degrees east, 18 degrees west up to 40 degrees east. Now, the first column here shows the moist static energy and the vertical, shows, okay, if I may explain better for us to know, the red lines are those for the WASP models. The black thick lines are for the observations. The blue are for the multi-model mean, the combination of all the 24 models. And then the green is for the best models. Excuse me. Now, same thing with the dotted lines. However, the dotted lines are for vertical velocity. Rather, the dotted lines actually are for the moist static energy, and then the continuous lines are for the vertical velocity. Okay, so if we look at this same feature, just like we have seen ahead before, you see that over the land between 18 degrees to 20 degrees east and 5 degrees to 15 degrees east indicates over the land. And then at the end here is for the entire region of study. So we find that in all that the models are actually not, especially the worst models. If you look at the red, the worst models in both the observation and if you compare the observations and the models, that you can find in the bottom plate here, which is the difference between each of the models and for each of the regions. Especially this point, you can find that the models are not the worst models are actually confined. The updraft is confined to lower levels of the atmosphere. There's no much migration. But if you look at the blue and the black here over this region as an example, you see that there is a better representation of this moisture and updraft, and then of the vertical profile of more static energy and the vertical velocity. So that is just a summary of that. And then I'll go to round off by giving you a summary of all that I have said so far, so we can have a conclusive understanding of what we have discussed so far, and then to conclude. So what is the mechanism and the implication in all that we have seen so far? Now, when you have a reduced downward radiation in the presence of stratocumulus clouds, what that leads it leads to SST cooling, and this SST cooling leads to an increase in the stability of the lower troposphere, and that leads to higher precipitation asymmetric index, and then it also encourages northward migration of the ITCZ into the continent, and then leads to a wetter continent. So this is a condition that favors the northward migration of the ITCZ. And then contrary, in the other way, if you look at here, when we have bias in cloud cover and reduced stratocumulus, the excess shortwave, we have excess shortwave. And then that excess shortwave leads to, enhanced cooling of the SITAO, that is the Southeast Tropical Atlantic Ocean, which warms up. And then that causes, the weak circulation. And then there is a decrease in stability of the lower troposphere. And that leads to the drying of the continent. And then we have lower precipitation asymmetric index. And then we have the stagnation of the ITCZ over the oceanic region. In conclusion, the study has shown that the tropical precipitation bias and asymmetries in CMIP6 models over the African monsoon rain belt results from a warm SST bias that can be attributed to the biases in the shortwave cloud radiative forcing. And these biases are actually can be attributed to the biases in the formation of stratocumulus clouds in the simulations. Many studies have pointed this out. And therefore, when we compare the zonal means of the shortwave cloud radiative forcing in the observation and the models, it shows a very, very significant difference, just like I've shown earlier. And we see that the models exhibit a stronger cooling effect due to clouds compared to in the models compared to those in the observation over land. So these discrepancies highlight the challenges in accurately representing cloud-related radiative processes within climate models and the importance of model validation and refinement for improved accuracy. Even though I may not have mentioned properly, but the resolution of models also contributes. Okay, so mostly in our study, we have found that higher resolution models equally show higher methods or higher assimilation of or comparison with observation. That still, the shortwave cloud radiative forcing representation in all the models is still a challenge to be understood. The biases in the CETAL causes the unusually warm SST during JJAS. As a result, the dry bias in the Sahel region can be attributed to poor circulation and moisture transport that we have seen, which causes the ITCZ to stagnate and then they do not migrate into the continent. And what that implies is that most of the models will be showing generally dryness over the region, and then that could affect our prediction in the future. So models with strong circulation over the continent and a lower CETAL SST bias tends to simulate better northward precipitation migration. The analysis shows that more static energy and in the mid and upper troposphere are less in the worst models compared to the best models. So this calls for the availability of in-situ observation, because you see, we are mostly using observational data sets or reanalysis from reanalysis, and we assume they are best fits. But that may not be comparable to in-situ observation data sets, which need to be overcome in order for us to get a better representation of models in our study. So this is one limitation that we have seen in this study. I want to thank everyone for listening while I am ready for the next segment. Thank you.
Thank you so much for this wonderful talk. So I think that we have some questions coming. Interesting talk. I wonder if the problem is related to the vertical resolution in the cloud layers. So I don't know if you want to comment on this a little bit more.
Very interesting question. Thank you very much for that question. Well, clouds generally are the major challenges. Assimilation of clouds are a major challenge in climate models because they are very, very difficult to assimilate in models. However, in our study, we have not looked at the different clouds layers to be able to see what actually happens. We just looked at the basics of this information and then see how that can relate to the stagnation of the ITCZ. Maybe and hopefully this can be something to be studied much in the future and see how these cloud layers can affect the migration of the ITCZ in the region or globally. Thank you.
I was actually going to ask you that, like, what is, because I know that from my presentation, like, you're willing to, to take the next step, right? A postdoc or a position to keep studying this. So I was going to ask you, is this the path that you want to follow, or do you think that you would be interested also in exploring other things within the same topic, more or less?
Yeah, thank you. Sort of, yes, it's an interesting topic to actually look at because subsequently we're going to do some sensitivity studies to actually understand better of why are generally most of the CMIP6 models not being able to assimilate this. So we can maybe in the future also go into that and then broaden the scope of study. Thank you.
Awesome. Okay, the next one is says the region where you computed the ITCZ did not include the entire Sahel region, which is between 10 north and 20 north. Do you think including the entire region will affect your conclusion? Did you analyze the Atlantic ITTC, which has been shown to influence precipitation across the region?
Yeah, thank you for that interesting question. This was also one question that we had to deliberate upon while waiting on the response from the reviewers. Actually, we have looked at this region of study. I'll show you. So while it's coming up, I want to indicate that the precipitation and asymmetry index was computed between 15 degrees south and 15 degrees north. And you can see, earlier explained that the precipitation asymmetric index is computed between 15 degrees south and 15 degrees north. However, it is not an arbitrary selection of the region, okay? The selection of the region is actually based on what TRMM gives us. So TRMM gives us precipitation during this season between around 5 degrees north up to about 15 to 16 degrees north, okay? So that's why we have just looked at this region over the season so we can give a proper conclusion to our study, okay? So we did not just choose that region arbitrarily. We have used that indication to see, okay, this is the region of maximum or more precipitation within our study area. And then that's informed our decision of checking that. So we check between the south, 15 degrees south, up to that 15 degrees north to be able to get a better conclusion. However, your question is appreciated. We will possibly look at what happens beyond 15 degrees 15 degrees north, if possible, in the future. Thank you.
Awesome. And I think that we have one last question. Thank you for a wonderful presentation. Do you think that moisture convergence over West Africa and Sahel are mostly controlled by newly localized Gulf of Guinea SST rather than SSTs at the Southeast Atlantic? And that's a question from Ibrahim.
Yes, to some extent, we have not completely ruled out the fact that SSTs within that region resemble that of the ENSO, okay? When you see that the characteristics over that region that I have shown, the bias actually resembles or mimics that of the ENSO. So studies have shown that this South Atlantic region is the upwelling region, okay? So over the Congo Basin, over the Atlantic, over the Southeast Atlantic, they have strong contribution over that region because without that is where you have the turning of the winds, okay, from south to southwest, okay. So that actually contributes so much to the moisture influx into the continent, and therefore we cannot completely rule out the fact that that region plays a lot of importance to the study. Okay. Thank you. Then another question says, how can this study impact Nigeria and Africa in general with respect to government policies and implantation for agriculture in order to fight food scarcity and hunger? Wonderful. This is a policy question. Unfortunately, I am not a policy maker, but I'll give a thought to this. Actually, why we are studying this is to prevent future events that could be harmful or that could be dangerous to the human lives, the economy, and then the general well-being of the people. So if you have too much of flooding or there is a forecast of too much of flooding given by the models, you can have a false alarm, okay? You can have a proper alarm. So a positive alarm or a negative alarm all depends on the prognosis of the models. So when you make a forecast and that forecast is being used by the farmers and it doesn't turn out to be well because there is no other way we can make use of forecast without models. So models tell us what happens in the nearest future, in the far future, and in the midterm future. So what that means is that if we are forecasting that there will be more rainfall in the future, so what will the government do? How prepared should the government be within that period? Are they going to move people to safe places or not? Or what policies will be put in place to prevent the adverse effect of flooding? So that is one way that this study can impact the nation. But beyond that, for us to be able to do this appropriately, we are advocating that data should be made available. Institute data should be made available so that we can have more accurate forecasts for the nation and for the growth of the country. Thank you for that beautiful question.
Well, thank you very much. I think that with this, we arrived to the end of this session today because I don't see any more questions. This was a really interesting topic, and we really much appreciate you joining us today and sharing your expertise and your work. And I'm sure that, well, if somebody has more questions or wants to collaborate, please reach out to him directly, or if you cannot find an email, like I can forward that if that's okay. So
Okay.
with that, thank you so much again. Have a wonderful rest of your day. For all of you that were connected, have a good morning or afternoon, Monday and week. And well, we'll see you all in the next Africa seminar. So thank you so much again for listening.
Thank you very much for your time.